Good day, Ma'am Liberty. Good day, classmates. We are the Group 2 and we are going to discuss the inner product spaces. I am Maria Miyaka together with my group mates, Miss Joessa Marie Bernal and Miss Angelina Bandojo. The objectives of this discussion is the first one, define and find the inner product, norm, and distance in a given inner product space. And the second one is demonstrate knowledge of general inner product space by applying properties of inner product. So what is inner product? Inner product is a mathematical operation that takes two vector or return a scalar quantity. It also known as a dot product or scalar product. We can let here that U, B, and W be a vector in a vector space B, and let C be an any scalar. An inner product on B is a function that associates a real number U, B with each pair of vectors U and B that satisfy the axioms. There are four axioms that we need to satisfy to call it inner product space. The first one is UB is equals to BU. Here, it doesn't matter kung ano maunang isulat or i-perform sa inner product space kasi the answer will be the same because we know that addition is a commutative. The second rule is UB plus W is equal to UB plus UW. Here, kapag kinuha natin yung inner product ng U B plus W ay same lang kapag kinuha natin yung inner product ng UB plus UW. And the third one is C scalar times vector UB is equal to scalar UB. Dito, we're going to separate the vectors into two and then we're going to attach scalar C in the first piece, which is C. And then B will be the same as it is. So it will be C or scalar C U B. And then after that, we can perform in any operation. And then the last rule is vector BB is greater than or equal to 0. And then vector BB is equal to 0 if and only if B is equal to 0. Dito, kapag kinuha natin yung inner product ng vector, the answer must be greater than or equal to 0. And then kapag ang inner product is equal to 0, ibig sabihin lang nun that vector itself is equal to 0 or 0. And then that's all the four axioms. And then we can say that a vector space B with an inner product is called inner product spaces. Whenever an inner product space is preferred to assume that the set of scalar is the set of real numbers. So, in sample 2, we need to show that the following function defined as an inner product on R2, where yung U is equals to U1, U2, and B is equals to B1, B2. Therefore, vectors UB is equals to U1, B1 plus 2U2, B2. Is the function U1, B1 plus 2U2, B2 is an inner product? To answer that, we must satisfy the four axioms. So, the first axiom is, kapag ba ni-reverse or inuna ko yung B, the answer must be the same. So, to show that, instead of writing it as UB, we're going to write it as B1, U1 plus 2B2, U2 is equals to BU. It satisfies the first axioms because we know that addition is a commutative. So, we're going to proceed the second axiom. So, in axioms 2, we're going to let W as W1, W2. Then, we're going to write it as U. B must be replaced as B plus W. So, it will be U1. Replace the B1 to B1 plus W1, and then 2U2, replace the B2 again into B2 plus W2. By distribution, it will be U1, B1 plus U1, W1, distribution again, distribute again the 2U2, and it will be 2U2, B2 plus 2u2 w2. By combining the like terms, it will be u1 b1 plus 2u2 b2 plus u1 w1 plus 2u2 w2. So the answer will be ub plus uw. So we already satisfied the second axioms. So the third axioms we need to show is how scalar interact with the inner space R with this vector space, the subscalar times the vector UB equal the scalar times the first and the second. So it will be C scalar times vector UB, and it will be C times or scalar times U1 B1 plus 2u2 b2 equals to, we're going to attach scalar to the first term or into u, and it will be scalar u1 b1 plus 2 scalar u2 b2, and it will be scalar ub. So we already satisfied the third axioms. And the last one is, we need to show that this vector is greater than or equal to 0. So if I take the inner product of a vector, so it will be vector b is equals to b1 squared plus 2b2 squared is greater than or equal to 0. For this expression is equal to 0 if and only if b is equals to 0. So we already satisfied the four axioms. Therefore, the vector ub is equals to u1 b1 plus 2u2 b2 is a inner product space. Now let us proceed to the third example, which is show that the following function is not an inner product on R3 where u is equals to u1, u2, u3, and b is equals to b1, b2, b3, where vector ub is equals to u1, b1 minus 2, u2, b2 plus u3, b3. It's much easier if we can proceed to the fourth axiom where the vector bb, it must be greater than or equal to 0. So we're going to let b equals to 1, 2, 1. Then it will be vector bb is equals to 1 times 1 minus 2 times 2 times 2 minus 1 times 1. By simplifying, we will get negative 6, where negative 6 is less than 0. So we can say that the function vector ub is equals to u1 b1 minus 2 u2 b2 plus u3 b3 is not an inner product.
Good day everyone, I am Juresa and I am the second reporter in group 2, and I will discuss the example number 4. In this example, we are going to take a look of the inner product on the set of 2 by 2 matrices. We simply multiply the corresponding entries together. Here in the example, A is being A11, A12, A21, and A22. And B is equal to B11, B12, B21, and B22. So we multiply the A11 to B11, then A12 to B12, A21 to B21, then A22 to B22. And after we are done in multiplying those corresponding entries, we have to add them together. And as we add them together, we will get the inner product of our 2 by 2 matrices. So that's it. And for our fifth example, we will look if functions can be and inner product spaces. In our example number 5, let f and g be real-valued continuous functions in the vector space continuous interval a and b. Let's use the vector notation f to represent f of x and g for g of x. These two are continuous functions on the interval a and b. Let's define the vector space of f and g as the integral of a to b of the product of f of x times g of x dx. Let me show to you the solution in this given example. Use familiar properties from calculus to verify the four parts of the definition. Number 1. The inner product of g and f is going to be the integral from a to b of g of x times f of x dx. So it doesn't matter which order we do first in that integral, we will always get the same thing. So the inner product of f and g is the same thing as the inner product of g and f. In number 2, let's try taking the inner product of f and g plus h. This will give us the integral from a to b of f of x times g of x plus h of x dx is equal to integral of a to b of f of x times g of x plus f of x plus h of x times dx is equal to the integral of a to b of f of x times g of x times dx plus the integral of a to b f of x times h of x times dx is equal to the inner product of f and g plus inner product of f and h. So here the integral of a to b of f of x times g of x dx is your inner product for f and g, while the integral of a and b of f of x times h of x times dx is your inner product for f and h. The third thing is multiplying scalar to the inner product f and g. It means that c as your scalar times the integral from a to b of f of x times g of x times dx is the same thing as the integral of a to b and move the scalar inside the integral times the f of x times g of x dx is the same as the inner product of c of your scalar c and f and g. The fourth thing, we have to know that the inner product is greater than 0. The inner product of vector and vector is greater than 0. Let's see if that works. The integral from a to b of f of x squared, we can say that it has to be greater than or equal to 0. Why? Because when we are squaring something, then it is or above the x-axis. And we can see here that the given example has met the 4 criteria. There are properties of inner products. Let u, v, and w be vectors in an inner product space P, and let C be any real number. In number 1, the inner product of 0 and v is the same as the inner product of v and 0 is equal to 0. And in number 2, the inner product of u plus v and w is the same as the inner product of u and w plus the inner product of v and w. And in number 3, the inner product of u and c times v is the same as c times the inner product of u and v. And now we will talk about the length distance angle. Let u and v be vectors in an inner product space V. The definition of the length of u as norm of u is simply as the square root of inner product u, and the distance between u and v is the norm of u minus v, and we have to use the square root of inner product uu to get the norm of u minus v. And the third one is the angle between two non-zero vectors u and v is given by the cosine theta is equal to the inner product of u and v divide the magnitude of u and the magnitude of v. And in number 4, the two vectors u and v are said to be orthogonal when their products is equal to 0. In example number 6, we will find the inner products of the polynomials. We have here the example of p of x is equal to 1 minus 2x raised to 2, and q of x is 4 minus 2x plus x raised to 2, and r of x is equal to x plus 2x raised to 2. Be polynomials in p sub 2 and find each quantity. So we will find the in letter A, the inner vectors of p and q, and b, the inner vectors of q and r, and c, the length of q, and d, the distance between p and q. So here's the solution. In letter A, the inner product of p and q, we will have to multiply those each term with the same degree. So here, inner product of p and q is equal to 1 times 4 plus 0 multiply by negative 2, where 0 comes, so negative 2x has no like terms in p, so that we will multiply it to 0, plus negative 2 times 1 is equal to 2. And letter B, the inner product of q and r is 4 times 0, since 4 has no like terms in r, and plus negative 2 times 1 plus 1 times 2 is equal to 0. So we will notice here that in letter B, the q and r are orthogonal. So in letter C, we'll find the length of q, and we know that the length of q is simply as the square root of inner product of q. So here we will get the value of q here is 4, negative 2, and 1. So we will square it. 4 raised to 2 plus negative 2 raised to 2 plus 1 raised to 2, and its square root, and its square root is 21. And letter D, the distance between P and Q is first we will put those terms in P on the length of 1 minus 2x raised to 2 minus 4 minus 2x plus x raised to 2 is equal to negative 3 plus 2x minus 3x raised to 2, and then equal to the square root of negative 3 raised to 2 plus 2 raised to 2 plus negative 3 raised to 2 is equal to the square root of 22. And that's, you will find those inner product and the length and also the distance between Q and R.
In example 7, we are going to solve using the inner product of C of 0 and 1, and the given function is f of x is equal to x and gx is equal to x squared. So in letter A, we're going to find the norm or the length of the vector within the vector space. Since f of x is equal to x, we can rewrite the formula for finding the length into the norm squared of f, which is equal to the inner product of the vector with itself. And using the standard way, the integral from 0 to 1 of f of x, g of x dx. And by using the integration, we have integral from 0 to 1 of x times x dx, and x times x, we get x squared. Then when we integrate, we can get x cubed over 3 from 0 to 1. And by evaluating, we now get 1 over 3, which means that the norm of f is equal to 1 over square root of 3. Now, in letter B, we are going to find d times of f and g, or the distance between f and g. So we can rewrite it as d times f and g squared, which is equal to the inner product of f minus g itself. Then we get the integral from 0 to 1 of f of x minus gx squared dx. And by substituting the value of f of x and gx, we now have integral from 0 to 1 of the quantity x minus x squared dx. And by simplifying, we get integral from 0 to 1 of the quantity x squared minus 2x cubed plus x raised to 4 dx. Then by integrating, we get x cubed over 3 minus x raised to 4 over 2 plus x raised to 5 over 5 from 0 to 1. And by evaluating, we now have 1 over 30, which is equal to 1 over the square root of 30, which means that the distance between the function f of x is equal to x and g of x is equal to x squared in 0 and 1 is 1 over square root of 30. We have here theorem 5.8, which is the list of the general inner product space version of Cauchy-Schwarz inequality, the triangle inequality, and Pythagorean theorem. And the proof of each part of the theorem 5.8 is parallels the proof of theorem 5.4, 5.5, and 5.6. And now in example 8, we are going to show on how to solve Cauchy-Schwarz inequality. So let f of x is equal to 1 and g of x is equal to x be function in the vector space 0 and 1. With the inner product defined in example 5, wherein we need to verify that the absolute value of inner product of f and g is less than or equal to the norm of f and norm of g. So, for the left side of this inequality, we have the inner product of f and g equal to the integral of 0 to 1 of f of x, g of x dx. And by substituting the value of f of x and g of x, we get integral of 0 to 1 of x dx, and by evaluating, we get x squared over 2 from 0 to 1, and by integrating, we get 1 over 2. And for the right side of the inequality, we have norm squared of f is equal to the integral from 0 to 1 of f of x times f of x dx, and we know that 1 times 1 is 1, so we have here the integral from 0 to 1 of dx, and if we integrate x from 0 to 1, we get 1. And for the norm squared of g is equal to the integral from 0 to 1 of g of x times g of x dx. And by multiplying x times x, we get x squared. So we now have integral from 0 to 1 of x squared dx. And by evaluating, we get x cubed over 3 from 0 to 1. And if we integrate x cubed over 3 from 0 to 1, we now have 1 over 3. And then multiplying the norm of f and norm of g, we get square root of 1 times 1 over 3. Then we get 1 over the square root of 3, wherein we have now verified the Cauchy-Schwarz. Next, we have here the definition of orthogonal projection, wherein V should be a non-zero or V is not equal to 0, then U can be a orthogonally projected onto V. And the given formula is the projection of U onto V is equal to the inner product of U and V over the inner product of V and V times the vector. We have here our last example, which is to find the orthogonal projection of U onto V. So the given vector is U equal to 4 and 2 and V is equal to 3 and 4, and using the formula on finding orthogonal projection of U onto V, we have 4 and 2 times 3 and 4 over 3 and 4 times 3 and 4 times 3 and 4 equal to 20 over 25 times 3 and 4. We get 12 over 5 and 16 over 5.